Professor Hu has been a member of the Institute of Advanced Study, Princeton, and was a visiting professor at Cornell University. Professor Hu's work in the 70s was on quantum field theory in curved space-time and early universe quantum processes, for which he was elected Fellow of the American Physical Society. He began work on non-equilibrium quantum field theory in the 80s, which resulted in a book with Dr. Calzetta by this title, published in 2008 in the Cambridge Monograph in Mathematical Physics series. In the late 80s, Professor Hu began his pioneering work on quantum decoherence in non-Markovian processes of open quantum systems, and in the past decade he has been studying quantum entanglement dynamics in atomic optical and superconducting systems with applications to quantum information processing. Please welcome.
Part of the effort of trying to understand one of the two very important elements in quantum information processing, i.e. decoherence, which of course we try to avoid as much as possible so that we would have a quantum system to manipulate to perform quantum information processing. And that, as in the introduction was mentioned, mainly occupied my attention in the 90s and of course continue on. In the last decade, we've started looking at the other important element, which is quantum entanglement. It's often said that quantum entanglement, of course, is the resource of quantum information processing because you can do parallel processing as mentioned in the earlier speaker. But it's also, of course, Schrödinger coined this word, I think, in his words, this is the uniquely quantum feature, i.e. you don't see this in classical physics, right? So in order to understand the foundational issues of quantum mechanics, I picked this topic because of these two reasons. On the practical side, of course, this is the resource for quantum computers, and to understand quantum mechanics a little better, I think we need to delve further into quantum entanglement. Now, you can see that even in the abstract and the first two lines here, I also bring in the important paper which is written by Einstein, Podolsky, and Rosen, the EPR experiment. It's a Gedanken experiment, it's a thought experiment, but it really challenges some of the foundation of quantum mechanics if you insist on understanding quantum phenomena from a classical mind, okay? And in fact, I think for most of us, that's always a challenge. That is, we're so accustomed to the classical phenomena that oftentimes we try to interpret quantum, phenomena and run into trouble. And I'll point out a few sort of problem spots or troublesome things in terms of, for example, the quantum non-locality. Okay, this is mentioned indiscriminately, in fact, by lots of people from AMO to quantum computing communities. And I'd like to clarify that a little bit, okay? And the spooky action, I think it was even mentioned in the EPR paper. And people usually view this as sort of a given state of affairs when you try to understand quantum phenomena. In fact, let me just mention one thing quickly to illustrate this. Oftentimes it's said that if you have a pair of up and down spin, right, atoms or any two-level atoms, systems, if you know exactly what the spin in front of you is, you could predict with exact accuracy what the other spin up or down is, okay? And yes, that's fine, right? Because you can have quantum states, right, constructed in such ways. But usually people just jump into the description that shows that there is non-locality in quantum mechanics. Okay, this word is used quite profusely. So, but if you think about it, where is causality, right? I mean, we also learn special relativity. Light propagates, or any sort of message propagates with a speed maximal at the speed of light. So how could you say that you can actually have information of the other atom at the boundary of the universe? Okay, this doesn't make any sense whatsoever. Okay, it takes finite time for information to propagate. And in fact, that's how we define locality, strictly speaking, in the quantum field theory sense. So in order to illustrate this aspect, we've carried out two sets of calculations in the last, even 10 years, 6 to 10 years, more focus in the last 5 years or so. Starting with the simplest case, with two qubits or two-level atoms, if you like, interacting not directly with each other, but by way of a quantum field. It could be a cavity field, it could be just one mode or two modes or a few modes, or a continuum of electromagnetic field. The emphasis here is in the common electromagnetic field. So you can see that this is pretty much the simplest possible setup, okay? And in fact, this is what you need to construct a quantum gate. So again, that's the simplest first step one really needs to understand. And I'd like to just show you how deceptively simple this problem is, okay? You can look at it at many levels. In the first level, you say, what? You know, haven't we known everything about this? At the end of the talk, I'd like you to, I hope that you will get up, this message that nothing, in quantum, nothing is simple, okay? It's deceptively simple only because you just don't know the hidden meanings, the different layers of structures in it. And it's quite, well, so for one thing, well, since the last 6 years or so, people have been looking at the temporal dependence, and that's why it's sometimes called entanglement dynamics, meaning the entanglement set up between two atoms or two-level systems. How does it evolve in time? So that refers to dynamics. But then more important, as we found out also, 06 was the first paper that we wrote, there's also spatial dependence, right? So if you take the conventional view that, it's never mentioned, in fact, that there's spatial dependence of entanglement. People just assume that it could be here, it could be on this other side of the moon, it could be on the other side of the universe. And you can have this kind of exact sort of entanglement. So in one word, I could just tell you that people, when they make that kind of statement, they're only looking at kinematics, just like setting up of state. There's no dynamics whatsoever because nothing is propagating. We know what's being propagated, of course, is the electromagnetic signal, okay? And of course, it will be limited by the speed of light. So you will see those results coming from here. And just to push this one step further, when the two atoms are outside of each other's light cone, I mean, this is a relativistic statement. What that means is they've never been in causal contact with each other, imagine. Somebody that you never know and you will in the future never know, okay? But you could establish entanglement with each other. You wouldn't know that you're entangled with someone else. So you need an intermediary to check on each side and find out that there is indeed entanglement, albeit for a very short duration. So this is really fully demonstrated, what the dynamics is and what the spatial dependence is. And so on the theoretical side, this provides really the theory for understanding the so-called quantum non-locality. You can continue using that term, but it's much better to understand what the context is, the content is, not just the context, okay? And so of course, on the practical side, as I said, this is really the first thing one needs to know. And overall, I came out with the feeling that we really don't know anything about quantum entanglement. Okay, so if somebody tells you big stories, ask him little questions. Okay, and you'll find that they will stop very quickly. Okay, I know there's a lot of smart, very creative, intelligent minds in India. From our students, we know. Just don't rush into things, because this is another thing. I'll say it and I won't say it again. Okay, in the States, funding everything pushes everybody at the speed of light to produce results, sensational results in science and so on. There are, needless to say, a lot of great results reported. But sometimes a lot of the issues were just shuffled behind, under the rug, or just pushed aside. There are really fundamental issues that we don't know much, and this way of doing science is counterproductive. Okay, people can be saying that again and again and again for 10 years. Okay, the money wasted. It's much better to just do things slowly. Okay, that's one remark I'll make to young people. Okay, especially. Senior people have the responsibility of getting funding and so on. All right, so there are two groups, and I would divide it into two parts. One is discrete variables, specifically about qubits, 2 qubits. The other part is about harmonic oscillators. So again, it's the easiest possible model that you could even get your hands on. So this is the next button. All right, that's the correct one. All right, so as I said, we are a tiny little group, okay, just pure theory, with a bent on foundational issues. That's under the JQI that Wendell had given such an eloquent and illustrative explanation of what it's for, its mission, and some of the ongoing work there is really quite exciting. For us, as I said, in the last 2 decades now, it's just 2 issues, okay? Very simple issues. But as I said, you really need to understand decoherence in order to come up with a quantum system to carry out quantum information processing. And in particular, okay, we pay a lot of attention to different models mocking realistic setups. Okay, so you give me a realistic setup, most likely you can use 1 or 2 or 3 different models to capture the different noises. So people usually would just say these are environmental noises that would decohere the quantum system. And of course, you need to understand the nature of noise in there. And in particular, sorry, make the mistake again. Is that, yeah, got it. In particular, our attention is focused on the so-called non-Markovian behavior. This might look like a foreign name and a foreign word to most of you, and me included. About in the 80s, I started looking into that direction. Simply put, it's memory, okay, with memory, processes with memory, okay? So let me just quickly turn this question around. Do you know of anything that could, process any meaningful information without memory? So if you think about it, non-Markovian science is not just in this field. It's really spread out, not just in physics, chemistry, biology, and so on, for the very simple reason that for most systems, you need some memory to operate. Okay. So far, people have only studied Markovian, meaning memory-less. Okay. And sometimes I'm teaching actually a course in this non-equilibrium thing. So if I give an example, several different cultures have different ways to deal with memory. Usually the old cultures like China, where I came from, and India, memory can get to such an extent that you can't move any further, any time steps. Meaning that, for example, you have to obey your husband, right? You have to obey your father-in-law, your mother-in-law, your ancestry, all the things that went back in history. And your conduct, what you say, needs to be consistent with everybody else, even though they might be inconsistent with each other. Okay? And in history, there are many tragedies. I mean, there's no solution, and you kill yourself. Okay? There are novels depicting those situations. It illustrates how difficult it is to deal with these processes, because usually you deal with, well, we're all technical, you deal with integral differential equations. Okay? Why is that? Because just consider two people, okay? The relation between two people, you get a feeling, okay? If I have my own dynamics, there's a dynamical time associated with me, for simplicity. There's another person that has there's a real person that has his or her dynamics. And if you are the one that takes the lead, so to speak, okay? The easy way to deal with it is just ignore that person altogether, right? The male society, dominated society, feminists would say that. That's why we need this revolution, okay? They just ignore us, okay? Now, if you look at it, it's actually two ordinary differential equations coupled, okay? Now, you say, I am the center of attention. The real way to do it, the truthful way to deal with it, is to turn the two coupled ordinary differential equations. You can always do that into one equation, right? It's a very nice equation governing my dynamics, but it's actually an integral differential equation, okay? The integral part takes care of the other person's dynamic in it, okay? And it's not easy to solve because it's very simple, right? Why do couples argue? Why, do states argue? Because each one has his own destiny. This is my destiny, don't lord me over. It's the same idea here, okay? But so far, most of the studies in physics, physical process chemistry, actually is better than physics, okay? In dealing with these processes, people just do the Markovian approximation. You can see how much off this whole thing is, how much off the true result when you impose a Markovian approximation. In quantum optics, people usually do that with a good reason, okay? But not so anymore in condensed matter physics, especially if the parties are strongly correlated, okay? There's just no way you can just cut it out and say, this part of the history, this is not a part of my concern, first of all. Secondly, whatever dynamics you have doesn't affect me. You listen to me, you go along with my dynamics, okay? So that's why, even though this big word stands here, it's actually what ordinary physical processes are, most of them. And I like to compare this with nonlinear science, let's say 20 or 30 years ago, okay? Before that, we always solved the harmonic oscillator. Whatever potential, in fact, there's a chapter in Goldstein, right? Small oscillations. You can always approximate it with a linear approximation. Well, why? Nature is not like that. It's only because these theories are really backward. They only know how to solve simple harmonic oscillator, okay? Nature doesn't run with linear science, okay? So nowadays, if you give anybody, okay, a solution which is linear, he said, what is this, okay? It's even simpler than what a computer, the simplest possible computer, can compute, which is nonlinear. Most phenomena, physical phenomena, involve nonlinearity. And I would say the same thing about memory, which is non-Markovian. All right, so that's the gist of the matter for us. And my talk has two aspects, two parts, I should say. Discrete variable, so the entanglement of qubits, and we use two two-level atoms as example. And the first part, immediately I just show you the variety of entanglement dynamics. Remember, this describes the evolution, time evolution of entanglement between these two-level systems, all right? Now, sudden death is probably some of you might have heard about this. In 2004, Yu and Aberle wrote a very nice paper in PRL stating that after a finite time, whatever entanglement that's established between these two qubits, okay, would die at finite time and would no longer appear. It would die forever. And so And you can imagine the funding agency would get really worried, okay? Because, as I said earlier, decoherence is, of course, something that spoils the fun, okay? You don't, if it's a classical system, forget about quantum information processing. Here, sudden death, again, is not just spoiling the fun, it just kills everything, right? No entanglement, no quantum information processing. So that's why the funding agency actually started funding some of these really useless theoretical studies. That's what we've been doing. It's useless because they think that we understand quantum entanglement, and under all circumstances, quantum entanglement are for free, and you can just assume that it exists in time, that you can carry out your computation. No, that's just not true. On the other hand, right, since then we also have studied a lot more systems that you can actually have revival, okay? Like, dead and then, coming back to life again. And you can even generate entanglement, from an initially separate state. There's no entanglement between the two, but the field actually helps the two to bring the two together, listen carefully, and then you can actually get entangled, okay? It's probably not too long ago, you still have arranged marriage, right? I mean, you sight unseen, your parents said these two should become, couples. It's a little bit like that, okay? They generate entanglement in you. Some people hate it, right? But you can see that actually a lot of things, the quantum field actually plays that role in here. You can also transfer entanglement, for example, between two atoms. If the two atoms were originally entangled, it can be transferred to the entanglement in the two modes in the field, and vice versa. That is, originally the two atoms are separated, right? Inseparable states are not entangled, but the field could help build up and transfer the entanglement in the field to the atom. It could also be protected from sudden death, meaning, well, of course, this is the parameter regime, right, that we should be looking for in order to carry out, even before you do a quantum computation or do any kind of design for it. It helps to find out which parameter regime would be the most helpful to do such a thing. Okay? You see, it's quite to my surprise that actually there's no theory work devoted to this. Okay? People just assume that, let's do that. Okay? So we carried out a detailed study in two models. One is two-level atom interacting with EM field. I should have said this to 1A rather. That's that's PowerPoint. So the first model we study is two-level atom and two field modes. Okay, that's mainly Kanu-Sinha's project. And then the second one, which was carried out actually a little bit earlier, that was the first project we finished 5 years ago. Took us 3 or 4 years actually to get that point, is interacting within the electromagnetic field with continuous modes. That is, you can go to infinity. That makes it a lot more difficult. The beauty in this study, which we just started about 6 months ago, is that you can actually get exact solutions. So it's simple enough that you can get exact solutions. I don't trust any approximation, okay? In fact, the rotating wave approximation, the Born-Markov, I've said it, but then also there's a couple of slides that will show you that for all the studies that carried out under these approximations without any kind of analysis of its validity range, just don't believe it. Just as a theorist, you should start out from first principle, from step 0, okay? And I'll tell you why many of the claims so far were just, well, if not erred, flawed, okay? All right, so the second aspect that's ongoing is carried out by Chris Fleming's PhD work, which is devoted to quantum open systems. And there are two branches, and the applied aspect is to atomic physics. We have made the analysis of the validity and of the rotating wave approximation, which of course is profusive, in fact, in the theoretical literature. While a good part of that lucked out, that is, a lot of the results that we believe are useful actually pass this test, but many others fail. And so what we have come up with is really the late time entanglement behavior, and without the RWA and without the Born-Markov approximation. So it's without using these approximations, this is of course a lot more trustworthy. So, right, the second part is about continuous variable, and I'm going to use this part to illustrate the EPR, the statement that I made earlier about quantum non-locality in quotes and spooky action and all that, okay? And it's mainly in collaboration with Suyun Lin in Taiwan, and there are two recent papers in PRD. One is the simple case of just two harmonic oscillators sitting there, like a lame duck, okay? Not doing anything, they don't even interact with each other, okay? The question is, if I give it some entanglement initially, what would happen at a later time? Fair enough, simple enough. Setup, okay, and even the calculation is not difficult, okay? Again, we're just surprised that nobody bothered to analyze that problem. What it turns out is quite instructive. Certainly I find it very useful to go through this kind of exercise. For one, you can see the distance dependence. There's a wave nature in it, in fact, just like constructive and destructive interference, as you can expect even intuitively with the message being sent back and forth mediated by the quantum field. The second one is what I just mentioned, that the two harmonic oscillators are never in causal contact, but there's a short duration whereby entanglement is generated, again, due to the intermediating quantum field, okay? Carrying that on with n qubits and n harmonic oscillators, that's also useful for atom arrays, and some of the experiments, in fact, were carried out for that. All right, so I've said this before, but let me go through this item by item. In fact, I should make an apology from the beginning after Wendell's colorful talk that really spanned the whole history of development and so on. By contrast, this talk is really dry, okay? I should have warned you in my first slide, okay? There won't be any movies, won't be any pictures, just pure thought. But again, I think this country has that tradition. You meditate for what? It's pure thought. In fact, better not to have any thoughts. You have reached the stage of gaining enough insight. What we're doing is, what I'm saying is that we need to go through that, okay, of doing the calculation in order to gather enough insight for us to address this really new issue, okay, even though it's been there for a long time, 80 years or more from the founding fathers of quantum physics. We haven't really looked into that yet. All right, so misconceptions and misunderstandings. That's probably one way to try to stir things up a little bit, okay? From some simple, that's a kind way of saying it, the unkind way is simplistic views on some key issues, right? So most people would say that the system of two qubits at rest is non-relativistic. Yes, for the motion of qubits, but they forgot about the quantum field that interlinks them. For example, cavity QED is intrinsically relativistic. In fact, I poked fun of our friend Jared Milburn when I was at the relativistic quantum information. I said, well, look, I mean, you guys have been doing cavity QED for so long, okay, carrying such a big name. How many people have really done QED in the fully relativistic sense, okay? It's basically trying to challenge them to take really the field a little bit more seriously, okay? If you do it, then you can get all the answers that I have related to you just now. The point is here that the action of the quantum field determines the causal relations of the two qubits, nothing else, okay? And remember, light, well, I mean, electromagnetic field, of course, we all know travels at the speed of light, but that's finite. So when you make a statement that it's at infinite distance, I could predict what's going on because of spooky action. Okay, just stop right there. And the main reason is because, okay, much of the quantum information is carried out by people who didn't need, okay, or still think that they don't need quantum field theory. Okay, that's why there's a big jump immediately, right? In fact, EPR were written in the context of quantum mechanics. Quantum field theory came a little bit later, not much, longer than that. But now we know, and we still don't want to do quantum field theory. That's the thing that baffles me. And this is really it's sort of baby step for people who know a little bit of quantum field theory. They could carry it out, or even if you don't know about field theory, but at least have the proper respect for the problem, you would have just gone down this road and get all these things that we said earlier, just now, okay? Dependence of entanglement on time, and let's go down the list. Entanglement dynamics behaves very differently for different quantum states. That's one thing we learned. And in fact, I'll show you a chart in a few slides. And there's also dependence of entanglement on the spatial separation of the two qubits. Okay, it's not like you can make statements about entanglement for qubits that are at infinite separation, spatial separation, or even space-like separated. Okay, so none of the above refers to quantum non-locality. If you want to be accurate about the meaning of non-locality, quantum field theory is local. Of course, quantum mechanics cannot be non-local, please, okay? If you want to do non-local quantum field theory, you might have to get to Planck scale, okay? I happen to have spent 2 decades on those things. So non-commutative algebra, non-commutative geometry, string theory, those contain non-local elements, and that's actually a very challenging, difficult, and counterintuitive situation. Okay, all the known physics, are local. Just that would be one way to say it. Okay, all right. So the implication of some issues at the foundation of quantum mechanics. Oops. I've mentioned this just now. What one can say and what is observed is quantum, entanglement and correlations between qubits, even in space-like separations. And so there's no sort of non-locality, nor acausality in quantum entanglement, and no spooky business. All right? Should have given this talk 1 month earlier in the Halloween time, so this is forward. All right, so I don't know if some of the earlier speakers have given you the background. I just assume that you know the difference between a separable state and entangled state, mixed state. And I just want to show you maybe this much, that for the measurement of discrete two-level atoms, there's a very nice quantity called a concurrence suggested by Wouters, and we're going to use that for Gaussians, for continuous variables in Gaussian states. Also, there's logarithmic negativity. I don't want to build up this whole thing on some measure of entanglement that's really not kosher or something, right? But these have been proven. Even if you go to 3 qubits, things get a little bit complicated. There are different suggestions. Not all of them are the same. Right, so let me just give you some illustration of what these behavior look like in different systems. This was the system studied by Yuan and Abele. They considered 2 atoms, 2-level atoms, sitting in 2 separate cavities. There's no electromagnetic field or anything mediating the 2, right? So they consider initially that these 2 systems are entangled, and then let it evolve in time, and they found that at a finite time, entanglement dies off and never come back again, right? So that's the statement. The concurrence function, I won't go into too much detail. You can represent the initial state with these 2-level atoms, right? 2-level atoms by a 4x4 matrix with a parameter A here which you can see from this plot. This is the parameter from, say, 0 to 1, and this is the concurrence. If it's greater than 0, it is entangled. If it's 0, it becomes separable. And this is the evolution in time, right? So you can take, this is just a parameterization, any vertical section here and follow the curve down. It started with this partially entangled state, entangled nonetheless, and then at finite time it drops down to 0. That's what they refer to, all right? So throughout the whole parameter regime, from 1 down to 1/3, they observe sudden death, because you can see that actually this line here, right, goes down to 0, finite time. But then from 0 to 1/3, it continues on further, right? So you can see already that, of course, the parameter dependence in there, as well as, of course, the dependence on the initial state. Now, there is also residual entanglement and entanglement revival. I'm just picking a recent paper by Juan Pablo Paz, who actually was at Maryland around 1989 and 1990. Did some work with me on open quantum system. But he's running a very nice group theory and a little bit of experiment in Buenos Aires. Now you can see, so this is continuous variable because there's two oscillators. And you can see here, entanglement drops down to 0, but if you're patient and wait a little while, miracles can happen, right? So there, you can explain religious miracle by some graphs even. Okay, here it is. Quantum entanglement certainly is quite miraculous in the sense that quantum can be so useful to us. Usually miracle makers need to have some practical value for people to believe in them, okay? They either get cured or they get funded. It's the same thing. So here's revival, entanglement revival. And you can also see that there is sudden death, but then coming back again. There are many of these things. In fact, what I'm going to tell you, okay, at the end of the story is that none of these things are really so strange, okay? Just like science today can explain many, many supernatural phenomena. And of course, it's a challenge to religion to keep on reinventing itself in some sense, okay? Which is good. It's a very helpful, healthy challenge or competition. Now, you can also have entanglement generation. I pulled this out from another recent paper involving chain spin, right? So qubits separated in space, but interacting through coupling with a spin chain can generate entanglement. This is, of course, because you do have a spin chain that interlink the two qubits is not that surprising. What's surprising is that it could actually be generated from the vacuum, okay? All right, so 2 qubits, I think I've said this already. So let's move on. So there are 2 groups of work, right? This is the 06 paper, which I'll give you a quick rundown. And then this is the latest work that's just been submitted about 2 qubits in interacting with 2 field modes, all right? Let's start with that, okay? Because this is a simple enough model, but it actually contains all the rich physics in it, okay? So the free Hamiltonian is just 2 atoms, right, in resonance with at least one of the modes. There are 2 modes, okay? If you just look at one, this is the field mode, right, with the frequency omega 0, and this describes the atom. I runs from 1 to 2, and of course the Pauli matrix, this is when the atom spits out a photon, jumps from an excited state to the ground state, and vice versa when it absorbs a quanta and gets excited in there. So in this blue box, it's a single mode, right, interacting with 2 atoms, and that can be solved exactly. Here is the second mode, right, and the 2 modes interacting with 2 atoms can also be solved exactly, okay, and I will demonstrate this quickly. And we've also, in the second paper, added a detuning in there. This is the simplest way to see the distance dependence. It's actually quite easy to understand because you shift any kind of phase shift, of course, has a corresponding distance measure, and so you can measure distance by doing the frequency shift in this rather simple model. And in fact, the phase here, right, as I just explained, is really in the k dot r term in a simplistic way, right? But you have two of them, that's why you can play around, right? It's not just k dot r, because you have a range here, and then you can see a corresponding range of the separation between the two atoms, okay? And indeed, in this case, we can do it perturbatively, right? Now, I mentioned that if you take the A1 and A2 and go to a transformed basis, really simply, it's the symmetric and antisymmetric combination of that. For the symmetric coupling, which phi corresponds to phi equals 0, it reduces to the coupling to a single transformed mode. So it's single mode, symmetric coupling. Whereas for the antisymmetric coupling, the other extreme of the phase condition, the situation is equivalent to the double James-Cummings model that Professor Hill mentioned just now. This very, very important, simple enough model, but it's double of that. So again, we could solve that exactly, right? So here is everything in one slide, because you can see that it's the DARPA funded thing. They gave us only 1 minute, right? Or 3 minutes. So here it is. So that's the interaction Hamiltonian. You can see sigma 1 A1, sigma 1 A2, I should say dagger, and then the same thing, but in here we've added a phase factor in there to carry the distance dependence. And this is the diagram for the transformation. It's actually quite simple. You can see that for phi equals 0, it reduces to this single mode symmetric coupling, and for phi equal to pi is a double James-Cummings model. So the first thing you notice, of course, is the symmetry of the system, and as usual, the qualitative behavior is governed by the symmetry over and above many other factors. This you may not be able to see too clearly, and I have a slide. The next slide actually blows this up, but if I just tell you a little bit what the columns are, initial field state and the atomic state, all right? So the field state, it runs, well, we've divided into the symmetric, this top part is symmetric state, the bottom part is the asymmetric coupling, right? What we call asymmetric coupling, symmetric coupling, single mode, two mode, double James-Cummings model like in here, and then two mode asymmetric coupling. Right? So with the symmetry division, we have these four types in there, governing the field, running down the vacuum state. The field is in the vacuum state, in the Fock state. In the state that's actually, you may not be able to see it down here, and in fact I could skip that for lack of time. Thermal state, coherent state, squeeze state, two-mode squeeze state. So it's pretty much everything that in the lab you can test. We actually would like someone someday to actually test these results, okay? Now, if you look at the atomic state, right, you can see that the yes-no here explains, right, indicates whether there is sort of entanglement right there, right, generation in an initially separable atomic state. That is miracle, right? If it's yes, it's miracle. If it's no, sorry, right? Now, so that's asking a little bit too much, right? So what we'd like to do in our capacity is to get to a state which is always alive. That state, the entanglement, is preserved throughout the whole dynamics or time evolution. You can see that there's sudden death in there, and we've also, SD stands for sudden death, right? And there's also a category called death at an instant, in fact, we could say a kiss of death, right? You almost die, and then you come back. This is faster than the revival. Revival takes some miracle worker or some medical worker to bring it back to life. This is really a kiss of life, of death. In fact, it drops down to 0 and comes up again, right? So you can have all sorts of things. You can see that, oops, all right, so here's blown up. You can see that slightly better. And now, this illustrates that, so you should be looking, if you are designing some quantum information processor, right? And looking from this chart, I wish more people would be doing a little bit of the hard labor, the theorists, I mean, to lay this out so people can see where to look for. You should be looking for yes, right? The first thing, yes, there's entanglement generation. And better yet, AL, always alive, right? That's what it is. Sudden death, forget it, right? And DI is acceptable because there's still an entanglement going on. And so you can see that here's entanglement generation, and here's entanglement protection, right? Because it's always alive. And you can also see in this case, is swapping, right? From the entanglement in the atom, in the field to the atom, right? So there's, you can see the interplay actually, if you look at this carefully, you can pick out which types of states in the field would be most conducive to imparting or engendering entanglement between the two atoms, all right? So this, I think, is probably the clearest of illustration with no hand waving that you can see all the behavior laid out. And let me skip all these details and go to the first part of my talk proper, okay? So these are the main features. Symmetric and asymmetric coupling lead to very different entanglement dynamics, symmetric coupling being more conducive to entanglement generation and protection. Always alive behavior arises in separable atomic states. Notice separable, even separable, right? But if it's symmetrically coupled, you can actually enjoy happily, living together behavior. And for symmetric coupled coherent and two-mode squeeze states, actually, you can perform this kind of miracle. Maximum entanglement protection for initially entangled state interacting with the two-mode symmetric squeeze state, okay? So entanglement generation from correlated field modes in the double Jennings-Cummings model via transfer. But there's no entanglement for uncorrelated modes, even though the origin modes may be correlated. You see, this is very detailed, even making the distinction between correlation and entanglement. Notice that quantum correlation is not enough, okay, to give you quantum entanglement. Quantum entanglement is more than just quantum correlation. All right, so this is, let me just show you this second project, which actually we started earlier in 06. And this is not limited to two modes, right? It's the same EM field. We want to see how the electromagnetic field induces entanglement between the two qubits. And here's the term that's worth noticing. It's always the k dot r term, right? So here is a continuum of modes. And just bear in mind that G is basically the coupling. We assume that the two modes have the same frequency, and in fact, if I show you the plot here, we're making omega 1 and omega 2 equal to each other, and it's from one of my very pure mathematical students that he actually began to make these plots, because this is what gives him jobs, okay? When he gives talks, he needs to show these things. So the distance between them, right, is I made a mistake again. The two-level atoms transition amplitude in a quantum field, temperature is T, damping is gamma. So back to the definition here. And in this calculation, we made a dipole and the RWA approximation, rotating wave. And I will tell you actually which part would need to be modified if you do away with the RWA. That is, if you want to be more accurate, certain features need to be modified, right? All right, this is a little bit too mathematical, so let me skip everything and just give you the results, all right? So I'm going through these slides because some theory-oriented students might actually find a challenge to go through this. This is again a model that you can solve, okay, albeit through some, well, we use, well, not me, Harris is my postdoc at that time. He liked to use Grassmannian for the spin for the two-level system, and then coherent state representation for the bosonic field, which is of course the photon field here. But let me just show you the master equation, right? So the mass equation in element form is a little bit easier to understand. So I've already skipped many things. The 1, 1 here and 0, 0 refers actually to the combination. Remember there's a field mole, right? We're assuming that is a vacuum in this calculation, and we denote it by a O, actually, which looks like a 0. And then the 0, 1 refers to the ground state and the excited state. And of course, we have 4 indices indicating the atomic state as well as the field state. So you can see all those indices there. These are the density matrices of the matrix elements of the reduced density matrix that's here. So once you know this equation, you can see how the whole system propagates in time, right? Evolves in time. That's why it's called master equation. In a more compact form, you can see that this is the Levelian term, right? The Hamiltonian plus the interaction Hamiltonian evolving in time. If it's a closed system, it obeys, of course, just the Levy equation. And this is in the so-called Lindblad form if you make the Markovian approximation. This is probably the most familiar to most people. So all that work that we put in several years is really just to get these two terms out, to flesh it out. And these are the off-diagonal non-Markovian components in this master equation. They are trace-preserving linear operators on the space of density matrices and so on, right? So what we need to do is focus on the dynamics here and see what new things it engenders and what could have gone wrong if you had ignored those two terms, as most people did, okay? All right, so the results are the following. The diagonal elements of the density matrix propagator, okay, decay exponentially, all right? This behavior is in accord to the results obtained by the Born-Markov approximation, which was in a paper published at the same time in 2006 by Fischek and Tanis, okay? We'll have more to say on this point later. The off-diagonal elements is what's new, and the new behavior in our calculation. They're different from the ones predicted from the Born-Markov approximation. How are they, right? So the source of this non-Markov behavior comes from the fact that, this is getting a little bit mathematical, that the coefficients are local in time and is not constant in time, okay? Meaning that at every point, in fact, the coefficient of the master equation comes from a solution of differential equations, coupled differential equation, right? So sometimes it's called a convolution-less master equation. So it's not just a number. If it's a number which is constant in time, you get the Lindblad form, which is what one gets using the Born-Markov or the Markovian approximation. In here, it depends on the initial conditions, certainly, and it also depends on history through the differential equation that the coefficients in the master equation obey, right? So those are the slightly subtle points. And so the behavior here also, again, depends on the symmetry. In the initial Bell state, right, the singlet state, as the qubits are brought closer, the decay becomes slower. This is one important aspect, that is, there is a benefit, okay, in terms of reducing decoherence compared to each qubit interacting with a field by itself. If you bring the two together close enough, the field actually builds up the kind of, well, maintains the quantum coherence better than if the atoms were alone in the field. Right? That's one thing we found out. In the triplet state, actually, the situation is almost the opposite. Right? And in fact, you can see in the plot here, this is singlet as a function of time measured by that decay constant. And R is the separation. So this is very close to each other. And under the Bell state, the singlet Bell state, you could keep the entanglement for a long time, much longer time. Okay? Whereas this, of course, when they are farther apart, we also expect the entanglement to drop down to 0, and that conforms to the sudden death scenario, as if the two were in two separate cavities. In the triplet, you don't have that aspect of that particular mode. All three of them actually, with different distances, had suffer the same fate of the decay of the concurrence in time rather rapidly. So you can see the symmetry behavior really dominates over. Another thing, well, at least it raised a few eyebrows of the referees, is that the spontaneous emission rate also gets modified, again because of the coherence effect or the sort of induced entanglement and enhanced coherence, quantum coherence effect when you have more than one atom along there. There's actually a quadratic decay factor compared to if each atom were considered the spontaneous emission rate is actually the square of each of these elements. Again, you can also understand because of the interference terms in there that could do good or do bad things to the system. Right? So let me jump now to the second part. Otherwise, we won't have time even to address the key issues. I have a few slides here. I'll just tell you what it is and then skip, coarse grain it over. With RWA, without RWA, okay, no RWA, okay, no RWA locality question, and there's a meaningful prediction about late time entanglement dynamics, right? So just this point alone, let's look at what that means, okay? If one uses, as most people have been doing, theorists, I should say, experimentalists are totally, exempt from that criticism. And in fact, in this field, I definitely trust the experimentalists, many-fold times more than my colleagues, theoretical colleagues. Well, because they have to do the work correctly, okay? And don't make too many claims in a very superficial way. Anyway, now you can see how terrible it is, right? There is order gamma error. That's pretty bad, okay? Gamma is the leading order, okay? All master equations equivalent to weak coupling perturbation have order gamma errors in the diagonal element values and late time asymptotic states, because most people make the claim when they settle down into stationary state, and people say, well, there is, at late times entanglement or no entanglement, but they are all off, right, missing an order, linear, leading order of diagonal correction. So the conclusion we made from this study, okay, which really was helped, right, by Chris Fleming doing a quantum open system study. He had 2 papers of each 80 pages long, so I don't think any referee would like to read it. But one spin-off from that really laborious study over the last 3 to 5 years is that, for example, when it's applied to this 2-qubit situation, there's no meaningful prediction about late time entanglement dynamics, like sudden death, except at high temperature. But that, as I didn't get to say, is not in the regime most conducive for quantum computing. Okay? So any claim really, needs to be scrutinized more closely with this kind of analysis. So the second part, as I said, is continuous variable. Okay, I'll just use 5 minutes to tell you the gist of the matter. Similar to the 2-qubit case, we have harmonic oscillators right in here, 1, A and B. And there's a coupling. There's a little bit of field theory here, no big deal. This is the motion, the trajectory of the particle. We leave it open, but you can set it just fixed, right, as in the case that I want to illustrate these results with. This QA and QB, everything remains the same, right? You can actually map it to the 2 harmonic oscillator QBM motion, which actually there is an exact form of the master equation given in this work. So this is the setup, right? So this is at the origin, and you have 2 harmonic oscillators symmetrically to the left and to the right, with distance d apart. And this is really a light cone, okay? This is time evolving upwards, right? I don't know whether there's some relativity students in the audience. This is how you can go to infinity because paper is limited, right, by the width, but you can have a roll of paper, meaning the stream of not consciousness but time flow, right? So this is from the first, this light cone, right, the original one, and so you can see that within this time, the two harmonic oscillators don't even know about the existence of the other, right? So it would have to wait till then that you say, aha, that's the star. Actually, most of the stars that we see today are dead, actually, okay, because it takes time for the light to come to our side, okay? In real time, it's not happening, right? So it takes that time. And in this calculation, the difficult part is really to get all these scattering, right, in there. So by this time, Su Yunlin stopped any further sort of calculation, finding out that actually this mutual influence is really not playing a decisive role in the qualitative features, right? This is another one just for fun. There's an unruled radiation and all that. So as I mentioned, there is a well-defined measure of entanglement for continuous variables. We need to do the partial transposition of the matrix, and so everything is well defined in here. And let me just give you the result, right? So this is quite interesting. In fact, let me give you this one. All right, so this is a plot, again, of time evolving and the separation between the two harmonic oscillators, right, in some suitable unit, okay, 5, 10, 15. So by changing the distance, well, first thing you notice, well, in fact, let me give you a better picture, enhanced, right? First thing you notice is that, so that's the light cone, remember? I just showed you the light cone. It's within the light cone that you can have causal contact between 2 points, right? So if you have the other oscillator situated, let's say, at 5 units from you, you would have to wait 5 seconds, let's say 5 meters, you have to wait 5 seconds in the unit that speed of light is equal to 1, okay, which we always assume to make life simpler. You have to wait till then before you actually feel the presence of the other person, right? Now, so you notice 2 things immediately. Outside of light cone, there are still these shades, right? The darker region refers to greater entanglement. So there is certainly existence of entanglement outside of light cone. Okay. The second thing you notice is this periodic, right, change of 0 or low entanglement to high entanglement to low and high, exactly like constructive and destructive interference, right? After all, quantum field theory, physical optics is an approximation of the quantum field. So you should, if somebody carries out a really sophisticated quantum field theory calculation and say there's no interference effect, just don't believe in him, okay? There should be such an effect, and it shows in a very nice way. The periodicity, of course, is governed by what the only frequency in the system, okay? So you can pretty much actually, if you open your mind, you can pretty much sort of come up with this kind of picture. But it's also interesting that you can see that it alternates, right? So here, the larger the separation, the greater the entanglement, okay? And so 1 minute would be finished, right? Good. So if you look at this, the larger the separation, if you increase in this direction, the greater entanglement, because the grayish area, right, starts to build up. By contrast, you go to here, the greater the separation, the lesser the entanglement. So there's no, you can't just say that I'm farther away from you, and hence we have less entanglement. There is this periodicity behavior, right? So this is also interesting, and in fact, this is my last slide, okay? So at short distances, late time behavior is a steady state, and there exists an entanglement distance. That is, if you come close enough to me, okay, it's almost like, I have some magic power over you, you and I would get entangled, okay, even though we didn't even notice each other. So there are two situations. The initial state of the detector, all right, if it's less than the entanglement distance, if the two oscillators are within that distance, If it's entangled, okay, then when it's greater, right, then it becomes separable. Right? But however, if it's just entangled state, to begin with, within the entanglement distance, you still have residual entanglement, right? So it's helping you within this distance. When it's outside, sorry, sudden death or finite time entanglement disappearance. If you start out with separable states, but if you're within this kind of protected zone, entanglement can be generated. Right? So that's really the summary of what I just said. And so what this whole thing illustrates, okay, is just two types of really simple model, the James-Cumming model with two atoms in there, with two modes in the first example I gave you, the second example with a continuum of modes. And you can already see a few things that non-Markovian behavior is absolutely important. That's sort of a new terrain that we just need to trot on sooner better than later. And then in this last example, that certainly causality is fully obeyed, everything is local, even though you can perform miracles like generating entanglement in two otherwise causally unrelated objects. Thank you.
We can take one quick question.
So I was wondering, what happens if instead of a bosonic bath you have a fermionic bath? Is that something you analyzed?
Are you in condensed matter related? Yeah. That's something I wanted to work on around the year 2000 with Harris and Anastopoulos. Of course, I mean, if we have all these Grassmannian and all that. We've started, but we have not gotten any sort of reliable result. But I'm usually very careful, I want to get everything consistent before I say anything. But of course, as you know, in the literature, there are many papers written already, right? Yeah. So we could compare some notes on that. And that, of course, is very important because a lot of the devices have fermion baths on them.